Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello and welcome to Physics with Beth and Beth. I'm Beth. This is our AP Physics C. We're still in this Unit 2 and we will be for a few more videos about Newton's laws of motion. We've already talked about forces, we've talked about free body diagrams with boxes setting on tables, a box on a table, and then a box on ramp. Today we're going to be doing interacting forces. That means forces that are tied together in some way, or in the next video, a couple videos from now, setting on top of each other, beside each other, but interacting. So in other words, we have a pulley system here in a block 1 and 2. They're on a table. It's a very common lab to do in class or in your lab class. And then we also have an Atwood machine that we're going to be doing both of these. And then the next video, we're going to be doing another one with a pulley system of a box on a ramp and combining the last video of ramps with this video of interacting forces, okay? So to give you kind of a heads up. So here we go, we're going to get started. We have mass 1 is 1 kilogram, mass 2 is 2 kilograms. The static coefficient of friction is 0.2, and obviously only block 1 has friction because it's the only one on the surface. Block 2 is in the air, and we're going to ignore air resistance. So there's only friction here with this surface. There's no drag or any friction with the air. All right, and they're wanting an expression for acceleration with givens and constants. Now, here's the 5 steps to doing these interacting. Very quickly, I just wanted to write them down and go over them. You do a free body diagram for each object. If you have 3 objects, you should have 3 free body diagrams. If you have 2, like in this case, we're going to have 2. Second, we're going to sum the forces as a system in these problems. And it's going to be parallel to the acceleration, which is really going to be parallel to the strings in both of these. And you'll see what I mean in a minute. You're going to define positive direction as the direction of acceleration. We're going to sum the forces using the second law, equals mass times acceleration. But since it's a system, it's going to be the total mass of both the objects because we're doing this as a system. Now, 5, if they make the statement, and they will in this unit, when we get to rotational motion in January, if you're doing this in high school, or closer to November, if you're doing this in college, you're going to find that this pulley will be massless until you hit the rotational unit, and then they're going to add mass so they can add some torque. All right, so, but in this unit, it will be massless. And what does that mean? If it's massless and there's no friction, it means that your tension on this object is going to equal the tension from the string on that object. Same thing, the tension here from this string is going to equal the tension here on object 2 from that string. Okay, perfect. And then something else that sometimes we tend to forget and think students know is that this string is going to be accelerating at the same rate. All right, that's why we can sum this as a system, because if this block is going to be accelerating just at the same rate as block 1 because it's all tied to the same string, they're interacting. All right, let's get started. We're going to start with our FBDs. It's not a disease. It's a good thing in physics. You can't do a problem and Newton's problem without them. Object 1. We have the block, so we make it a dot. This one has tension to the right because we have a string. I'm just going to call that capital T. A lot of times they do the capital T there. We'll keep that. All right, we have force due to gravity down. So I'm going to do that. Force due to gravity of 1. You're going to keep subscripts on these. It's really important because the mass of 1 is not the mass 2. So you can't just put Fg or weight there. Some people will use a capital W. That's fine too. All right, I just like to use force due to gravity, so when we get to the work unit, it's also a capital W. But I'm putting a 1 here to recognize that that is 1. That is not the mass of 2, okay? All right, it's on a surface. This is on a table, so that means there's a normal that is straight up. Let me try to make that equal here, because those are balanced, because it's not moving. In the vertical direction, it's only moving this block in the horizontal, okay? Now, block 2, and then we're done and ready to do this problem, is I have my little dot here for block 2. I've got tension up, and that tension I said is equal, so I'm going to try to make these about the same length. Maybe, I'm hoping that was force due to tension there. Hopefully those are the same length, because remember I said they're equal because this pulley is massless and no friction. Should have said that, but massless pulley. They will be in this unit. All right, and then the only other force I have on this one is force due to gravity, and it must be longer, and I'm going to put a 2 there because it's the mass for block 2. This one must be longer than this tension because it is moving in this direction. This block is moving down. This block 1 is moving to the right and block 2 is moving down. Now, if you noticed, I had a coefficient of kinetic friction on block 1 on a surface. So I am missing a force over here, and it's friction, and it's kinetic because it's moving. Now, why did I make it shorter? Again, these forces must be unbalanced towards the east because this block is moving in this direction, and then the bottom block's moving down. Okay, we're going to define as positive direction. This way, that's my positive direction. Okay, now we've done the free body diagrams, check. Now it says sum the forces as a system parallel to the acceleration or parallel to the string. So this is all of these forces. So let me get a little red marker here. This force is parallel to the string. This force is parallel to the string. This tension, in this block, we have force of tension is parallel to the string, and so is force due to gravity of block 2. These are the 4 forces that are parallel to the string in both instances. And it's kind of hard to see because this is horizontal and this one's vertical. But think of parallel to the acceleration, if that helps, because that's really what it is, parallel to the acceleration. All right, and remember that's total mass, and then that's that parallel acceleration. So here we go, we're going to get started. Remember, I defined this way is positive for this one, and this way is positive for this one, the direction of acceleration. So force due to kinetic friction is, the force of friction is negative. My force due to tension here is positive. This force due to tension is negative because it is not in the direction of acceleration. So there's a minus force due to tension. All right, and then I have a plus, because this is in the direction of motion, force due to gravity of that block 2 equals total mass. That means mass 1 plus mass 2, total mass times your parallel, your acceleration, parallel to that string. Okay, some things to note. Remember, keep your subscripts. Now this feels weird for many reasons. One, it feels weird that horizontal east is positive and then south is positive, but don't think about your old terms. It's direction of acceleration. Second, it feels weird that this force due to gravity at block 1 doesn't affect acceleration, but it doesn't because it's perpendicular to the direction of acceleration, so it doesn't affect it. All right, so that's why it's not in here. The second thing that feels weird is making this force due to gravity, because down is always usually negative. It feels weird making it positive, but remember, we're defining direction of acceleration as positive. All right, the next thing we said, and you make this statement with the AP, hey, we know that T1 equals T2, because that, and I went with my tension here. Let me do it this way since I started this. 1 equals force of tension 2. Okay, because again, massless pulley. So look, positive and a negative, so they're gone. So we have negative kinetic friction plus force due to gravity 2, and if we can remember, that's just m2g, so I'm going to put m2g equals m1 plus m2 over my acceleration. All right, the only thing now I need is an expression for friction, because it's going to be givens and constants. I was given mass, I was given little g's. So, and I want acceleration. The only thing I need to do is figure this out. Well, here we go. We know where we're going because we've done this enough now. The friction, physics is fun. We have a formula to prove it. All right, here's my kinetic. Okay, so I know my mu, it's a given, so I'm going to put mu, but I need my normal. Okay, I'm looking at this block, the only block that has normal and the only block that has friction. That's why I'm dealing with only block 1 here. Is because it's on the surface. I've got normal. Well, look at this. Normal has to equal force due to gravity of block 1. They are balanced forces because this block is not moving in the vertical direction at all. So really that's equal to m1g. Now that was a little bit of a shortcut, so let me back up and say, hey, I could sum the forces perpendicular to acceleration on that block 1. Okay, you could just call it y if that makes you feel more comfortable. On this again is only on block 1 is mass times acceleration in the y, but acceleration in the y is 0. The block only moves east, not north or south. So we have normal up minus force due to gravity 1 equals 0, because this whole thing's 0. Well, normal equals force due to gravity of block 1, and that's going to be m1g. All right, so now we have an expression for our kinetic friction right here that I can put in. So it's negative mu m1g plus m2g equals m1 plus m2 times acceleration. All right, now I'm going to divide both sides by m1, m2, and I get negative mu m1g plus m2g divided by m1 plus m2 equals my acceleration, and that, my friends, is your expression for acceleration. If you were to put numbers in here, that's 0.2, mass is 1, 9.81 plus mass 2 is 2 kilograms, g is 9.81 divided by 3 kilograms, because that's 1 plus 2, so divided by 3, I should say, equals acceleration, and your acceleration is going to equal 5.89 meters per second squared. All right, now the next thing they might ask you is for tension, and you're like, we canceled out tension, so how do we figure out what tension is? Okay, you take one of the free body diagrams and just do one object instead of a system. You could do either one and you're going to get the exact same answer. I could do this block and get the same answer, or I could do this block and get the same answer. I just picked this one for the fun of it. All right, so I'm going to switch colors so you can see this, and I'm going to go down here. I'm actually going to delete this. Delete. I'm erasing. I'm using an old school dry erase board. There's no delete. All right, so object 2, I have up is, okay, I'm going to call the direction of acceleration positive. So this tension is opposite direction. So I'm going to sum my forces parallel to that string for object 2 only. So that means the mass of this is going to be for only object 2. There's no adding masses now because I'm not doing it as a system. Okay, so I have a negative force due to tension plus down in the direction of acceleration is that force due to gravity for object 2 equals the mass of object 2 times the acceleration. Okay, I want tension. This is what they're going to be wanting is tension. So I'm going to solve for tension. So I have force due to gravity or weight of object 2 minus, because I'm going to subtract this over, m2 times the acceleration that I just solved for, and I'm going to add force of tension over. I just added force over, subtracted this expression over. That's m2g minus m2a equals force of tension on object 2. All right, well, I know mass 2 is 2 kilograms, g is 9.81 minus 2 kilograms, and acceleration is 5.89. And that's going to give you a force of tension 2 of 7.85 newtons. Okay, well, plus we have an expression if they ask for an expression. Now, it wouldn't have mattered if I had done block 1 and I would have had, this would have been positive tension minus the friction force equals mass of block 1 times the same acceleration, because they're accelerating at the same amount. You get the same answer. Doesn't matter which block. Okay? All right, now Atwood machine, really quickly, we'll move on. I'm going to stick in here a photo, or I'm going to try, now that I've said it, I have to, of a antique Atwood machine, because a lot of times people keep drawing these and they're like, I don't understand what it's used for. My engineering runs in my family. We have many engineers in our family. And my great-grandfather was no exception as far as being a mechanic. So he had this great Atwood machine that my nephew has just installed in an awesome treehouse for my great-nephew. So I'll be including that. So you can see what an Atwood machine looks like. And it's an antique one that's pretty cool, if you ask me. Anyway, all right, so Atwood machine. What happens is you've got an object here, you've got an object here, and this is moving to the right. How do I know that? I'm telling you that. But block mass 1 is equal to 2 kilograms and mass 2 is equal to 4 kilograms. I Hey, check that, make sure that's what I set it up to be. Yes, I did. Okay, perfect. All right, so it's at rest at start, and then you let go of block 2, and it falls down, it goes down, and block 1 goes up. Okay? They're going to want that acceleration and tension 1 again. Again, same thing, interacting blocks. Free body diagram for each. So here's my block 1. I have tension that's up. I have force due to gravity that is down for that block 1. Unbalanced because this thing is moving up. So this one needs to be shorter. Your weight needs to be shorter than your force due to tension. All right, block 2. Block 2, T1 and T2 are going to be equal because they're going to tell you this is a massless pulley because in this unit, it just will be with no friction. All right, so these have to be equal length. All right, and then, but this one is moving down. It's going to need to be longer. I probably exaggerated that a little bit too much, but unbalanced because this one's moving down. That's it. We do the same thing. Sum the forces parallel to acceleration, and we're going to define this way as positive. So here, this block's going up, so the direction of acceleration is positive. This block's going down, so again, the direction of acceleration we're going to call positive. Okay? So just think of it going all the way around. If it's moving in that direction, it's positive. So we're going to sum our forces parallel to the string, and then we're going to use it as a system. So that means total mass. Okay, I'm just going to bend down and get this eraser here, and I'm going to mark these off so you can see that. So here we go. First block, block 1. This is block 1. This is block 2. Okay, we have tension up. That's in the direction of motion. So we have force due to tension 1 minus force due to gravity 1 minus that force due to tension here for 2. I'm going to call that 1 and 2. For 2 is opposite the direction of acceleration, so it's going to be negative. Force of tension 2 plus, this is in the direction of acceleration, so that's going to be plus force due to gravity of 2 equals m1 plus m2 because it's total mass times that acceleration. You're going to need to make the statement that tension 1 equals tension 2 because it's massless, so those go. That's a positive and a negative. We have negative force due to gravity 1 plus force due to gravity 2 equals m1 plus m2 times acceleration. That's just negative m1g. That's plus m2g. Divide both by m1 plus m2, and you get your acceleration. All I did was put in, remember, force due to gravity is m1g, force due to gravity 2 is m2g. I subbed those in, and then I divided by both masses. Okay? That's your expression. If you were to put in your numbers, 2 times 9.81 plus 4 times 9.81, and that was negative, over 6, because it's 2 and 4, so that's over 6. Your acceleration is 3.27 meters per second squared. Now you have the same problem. They're going to come back and ask for an expression for tension and a number for tension, usually. And you're like, I canceled out the tensions. It's okay. Go back to one block. Doesn't matter which block. We even have the same amount of forces, so it really doesn't matter. I'm just going to go with the first one. So I'm going to do block 1 only. Up, that's the direction. I have force due to tension 1 minus force due to gravity 1 equals mass, because this is the sum of the forces, I should tell you, that is parallel with the string, but only for block 1. And that's going to be mass of 1 times its acceleration. Okay, I'm looking for that tension force, so that's m1 times my acceleration plus m1g, because, well, here, I won't skip that. I'm going to add the force due to gravity 1 over. Okay, all right, well, that's m1a plus m1g equals that force of tension 1. All right, well, we put in mass 1 is 2 kilograms, 2 times the acceleration, which was 3.27, plus 2 times 9.81, and you're going to get a tension force of 26.16 newtons. And if you were to do that with this one, you would get the exact same answer. Just don't forget, this tension here, though, is not in the direction of acceleration, so it's not our positive direction, so that's negative, and that's positive force due to gravity 2. Equals m2, because we'd be working with only block 2, times that acceleration that we found. And you get the exact same answer. Doesn't matter which block. All right, that's it for interacting forces with these strings and pulleys. And thank you for watching. If you haven't subscribed yet and you're liking these videos, we would love for you to subscribe, and then you'll get notification when we post new ones in this unit. Also, if you have peers that are taking this class with you and these videos are helping you, we would love for you to share with them. And thank you for watching, and happy physicsing.